Hey guys, Mr. B here, and in this video we're going to be going over the chapter 10.2 questions. So if you're having any issues with that, hopefully this video will help you. Alright, here we go. Number 1. In your words, define the terms relative age and absolute age. Alright, so relative age it usually just means something that's older or younger than something else. There are no numbers involved. Okay, it's not a guess. It's not an approximate, it's not an estimate. There's no numbers. It's just that's older than that. That's younger than that. That's it. Okay? Absolute age includes numbers and is usually an estimate. It is not exact. Okay? Absolute ages are not exact ever. They're always a time span. So we're going to put down something along those lines. Let's make our font a little bit smaller here. So let's say relative age is a comparison of two things. Usually saying one is older or younger. No numbers. Absolute age includes numbers and is usually an estimate or approximate. All right. Number 3, and actually, you know what? I'm going to put question number 3 here on the next. We're going to do a duplicate slide here. We're going to put number 3 there because I'm going to run out of space, I feel like. So let's just copy this over. Yep, let's just delete all this. There we go. Perfect. All right. Number 2. What is the law of superposition? So the law of superposition is the law that states that younger rock layers are found on top of older rock layers, which are found on bottom. Okay, so you can say the law of superposition states that in horizontal rock rock layers, older rock layers are found on the bottom, and younger rock layers are found on top. All right. Number 3. A geologist finds a cliff where the edges of several different rock layers can be seen. Which layer is the oldest? Explain. All right, so this basically is exactly just the law of superposition. We had just mentioned that, so we can say that the oldest rock layer is going to be on the bottom, and the youngest rock layer will be on top. This is because the older rock layers are laid down first, and the younger rock layers are deposited on top. And you say law of superposition. All right. Number 4, besides the law of superposition, what are 3 types of clues to the relative age of rock layers? All right, so remember that the law of superposition is not the only thing that we use to determine the age of rock layers. So what are some other things that we talked about in the notes? So just to remind you, we talked about intrusions. We talked about extrusions. We talked about fault lines, unconformities, and index fossils. Okay, so there are actually quite a few things that were mentioned, but these are just some. And then it only asks for 3, but I'm just going to name all of them. So compare and contrast extrusions and intrusions. All right, so compare and contrast typically is like what's similar between them, what's different. So similarities. Both are igneous rock layers. Okay, so similarities is both are igneous rock layers. An extrusion and intrusion is both where igneous rock pushes its way up, typically through sedimentary rock. Okay, so they're both igneous rock layers. The difference, however, or differences, are that extrusions is when the igneous rock breaks through the surface and then is deposited on the surface. And intrusions is where it pushes its way up, but it doesn't break the surface, so it stays underground. Okay, that's primarily the difference. So extrusions break the surface and get layered on top. Intrusions don't break the surface and stay underground. Okay, there we go. All right, an intrusion crosses an extrusion. Which layer is the older? Explain. Okay, so this is an interesting one. So if we have an intrusion, so an intrusion again is pushing its way up through rock, and it's crossing an extrusion. So an extrusion would be, so let's say a rock layer, an intrusion or igneous rock has pushed its way up, and it's pooled on the surface. And then we have another rock layer that's pushed its way up, and it's cutting across that one. Which one is older? Okay, so this is the principle of cross-cutting. So if we have an extrusion that has pushed its way up through rock layers and it's deposited on the surface, and then another intrusion comes up and cuts its way through that one, that means that the extrusion is older because it was there first, and the intrusion is younger because it cut its way across that one, and that one had to be there first in order for this one to cut through it. Okay, so we are going to say that the extrusion is older because the intrusion is cutting across it, and the extrusion needed to be there first in order for the intrusion to be able to cut across it. Okay, this is the principle of cross-cutting. Okay, which basically says that an intrusion is younger than anything it cuts across. So, all right. Number 7, what is an index fossil? All right, so remember that we talked about index fossils in this section of notes as well. And an index fossil is going to be a fossil of an organism that typically lived for a relatively short period of time. And we can use that fossil to determine what layers of rock are the same age as each other. Okay, because that organism being alive for only a short period of time, if it's found in other rock layers, then those rock layers all must be the same age. So we're going to say something along those lines. We'll say that an index fossil is a fossil of an organism that was only around for a brief amount of time. It can help geologists to determine if rock layers are the same age as each other. Okay, something along those lines. All right, last question here. The fossil record shows that horseshoe crabs have existed with very little change for about 200 million years. Would horseshoe crabs be useful as an index fossil? Explain why or why not. All right, so 200 million years is a pretty long period of time. The geologic time scale is like 4.5 billion years. And 200 million years is like pretty much, long period of time. So I would say probably not. I would not say that they are a good, useful index fossil because 200 million years is too long of a period of time. If it was maybe 10 million or 50 million years, probably would work better. So I'm going to say no. Horseshoe crabs would not be useful as an index fossil because they were around for a period of time that was too long for them to be useful. Okay? Something along those lines. All right. That is it for this section of notes. Hopefully that helps you. And as always, if you have any questions, you can always email me or reach out. All right, guys, that's it. I'll see you in the next section. Bye.